So, okay. Well, thanks, Ella, for the opportunity to talk here to the people from VLab. And I'm going to talk about this construction of symplectic foliations on three-dimensional orientable Riemannian manifolds. The idea is to take a harmonic two form and out of it construct a foliation, and this two form is going to restrict itself to a symplectic structure on each of the leaves of this foliation. The constructions I probably know, so probably not many people know it, but the people who knows it, who know it, they probably know this very well. So the setting is the following. We start with a three-dimensional orientable Riemannian manifold, okay? And we need the Riemannian structure, and it's either going to appear explicitly, like something in this formula here, which is as the Riemannian structure appearing explicitly, or it's going to be appearing implicitly.
Alfonso has just arrived.
Okay.
Hola, Alfonso.
Hola.
Bueno, tú estás familiarizado con todo este asunto, no te hace falta.
Okay.
Bueno,
so yeah, I'm just starting with the setting. So the setting is a Riemannian manifold, okay? And the Riemannian structure appears either explicitly on the constructions, or it's going to be appearing implicitly through the hard star operators, okay? I need orientability because most of the time I'm going to compare, we're going to have some structures, they're going to be positive or negative with respect to the orientation given by this Riemannian structure. And the three-dimension is also very important because some relationship between the hard star operators, they are only valid in dimension 3. So those things are really important. Right? We cannot extend this, anything that I'm going to talk here about, to 4 manifolds or 5 manifolds. Even though there are extensions to those manifolds, the main results really do not follow. So if you've never seen a hard star operator before, yeah, that's all you're going to see in this talk. It's going to be this slide. But you can actually get all the information to define them even from these relations. But do not worry, you can easily find information about hard star operators. What you need to know now is that they take K forms and take them into 3 minus K forms. Okay? The 3 here is regarding the dimension of the manifold. And if you apply them twice, those are linear operators. Okay? If you apply them twice, they're going to give you the identity. One property that's really useful, and we're going to use a lot here, is the fact that if you take the constant function equals to 1 on your manifold, and you take the hard star applied to that function, it's going to give you the Riemannian volume. And this is the thing that we're going to use to measure everything. Okay? The next 2 properties, which are really relevant in three-dimensional case, is the fact that you take 2 forms into 1 forms, and 1 forms into 2 forms. Okay? And this is what we are going to use here right now in this line. So if we start with our 2 form, okay, alpha, we can take the Hodge dual. So once you apply the hard star operator to a form, you usually call it the Hodge dual of the form. So you can look at the Hodge dual of this 2 form. This is going to give you a 1 form, because we're in dimension 3. And you can take the dual vector field with respect to the Riemannian structure. Okay, this X is the dual vector field, which makes sense because, well, this is a 1 form and this is a vector field. So the Riemannian metric does this for us because it's not generated. And out of these 2, so you have these 2 formulas. So you have that alpha wedge, the product of alpha with its Hodge dual, it's going to be proportional to the Riemannian volume, and the function, which is the constant of proportionality, is going to be the norm, the square norm of the vector field here, the dual vector field. And you can actually recover the 2 form out of contracting this vector field with the Riemannian volume. Okay? So you can, it's possible to use these two properties to define the hot star operators if you've never seen hot star operators before. But I'm
Sorry,
not going to.
Romero.
Okay.
There's like a D missing. Or something.
D.
No,
Yeah.
sorry, not a D, a star missing in the second equation. Like the last equation, alpha equals.
No, it's okay. It's correct. So the two form, take the three form, which is the volume form. Okay, so you take the Riemannian volume form, which is a free form. You contract it with this vector field here, and it's going to give you a two form. And the two form is exactly the one that you start. So the one from.
Yeah.
Okay. No, it's okay. Now, what's the structure that I'm really interested in? So, I'm interested in taking a two form, okay, on your manifold. So we have this Riemannian manifold that we started with, and we put a two form there. And I want this two form to be non-vanishing. It's actually, I'm gonna have examples with it like vanishing at some points, and it's actually not important that it vanishes or not. But I'm interested in the behavior around the points where it does not vanish. Okay, so you take a two form which is not vanishing, and it's closed. Okay, so the exterior differential of this two form is zero, but as well the exterior derivative of this of the Hodge dual of this two form. Okay, so this one form here, if you take the exterior derivative, is zero again. So it's what we usually call co-closed. Okay? But this is an example of a two form which is harmonic. Okay, and it's tied to Laplace's equation and blah blah blah. This is what we call it harmonic. So if you have such a form, okay, a two form which is closed and co-closed, what you actually have, it's a foliation, a symplectic foliation on the whole manifold. And let me explain how it goes. So if you're assuming that the two form is not vanishing, then the Hodge dual will respect that. So you take the Hodge star operator, it's going to take something which is non-vanishing to something which is still non-vanishing. So the Hodge dual is going to be non-vanishing as well. This means that the kernel of this one form, okay, it has constant rank, and in this case it's dimension 2, because we are at the one form on a three-dimensional manifold, so we have dimension 2 for the kernel. And the fact that we are asking this one form to be closed means that this kernel here gives us a distribution which is integral, okay, for this theorem. So we have a foliation. We have foliation by surface. And of course, there are surfaces, so surfaces are symplectic manifolds, but what is non-obvious here, sort of, is the fact that if we take this two form here and restrict it to the leaves of this foliation, you're gonna get a symplectic structure, okay, on each leaf. And this comes from the fact that you're asking beforehand that these two forms to be closed, but also since this thing it's non-vanishing and its Hodge dual is also non-vanishing, the product is non-vanishing, so this gives us a volume form, and this will provide the non-degeneracy that we need to prove that this thing is symplectic on each of the leaves of this foliation. Okay. What else we got? We got that the tangent space at each point of our manifold splits orthogonally into the kernel of the two form and the kernel of the one form. Okay. And here you can see how it goes. So if we define a vector field, I call it, well, R is because it's related to the red vector field of the theory, and it's also, in example, is going to be the radial vector field. Okay. So if R is the vector field satisfying this equation here, so it's dual to the Hodge dual of the two form. Okay, there's a minus sign here, but it's not that relevant. Then the kernel of the one form that you constructed of your two form is going to be exactly this, the orthogonal complement to this vector field R. Okay? And from lemma 1, you have that the two form, it's actually written like this. So the contraction between this R vector field with the volume form of the Riemannian volume form, then this means that the kernel of the one form is actually generated by this vector field. Okay. And finally, because this is going to be really relevant, the volume form that you generate by multiplying the two form and its Hodge dual, it's proportional to the volume, to the Riemannian volume form, and this means that the symplectic leaves of this combination, they are positively oriented with respect to the Riemannian structure. Okay, so this is really important. That you have these positivities of the leaves. A really small example of.
Something.
Sorry?
Can I ask something?
Yeah, yes.
So if you have instead of this harmonic two form, if you have a pair of closed forms, so a one form and a two form which are closed and whose wedge is a volume form, then you can find a metric that makes omega the Hodge dual of alpha. No? Is it true?
So I will talk about this in the next slide, but actually we start with a Riemannian metric, and then we look for the two form there, which has this property that it's harmonic with respect to this Riemannian metric. But yes, in some cases you can start with the form and then find the Riemannian metric such that this thing is going to be harmonic. And this is what I'm going to talk in the next slide. Did I answer your question?
Yes, thank you.
Okay. So,
am I the only one who is here listening so bad to Romero's sound?
I
It's
hear
like
the noise, but I hear Romero as well. I think the noise is.
Yeah, I don't know. The rear noise is too high. Like it's very hard for me.
I will try to speak louder and lower the microphone
I don't know.
volume
Yes.
to see if. Yeah, I think it's
Okay.
the internal fan of the.
It seems so, yes.
I'm really sorry for that. I have no idea how to solve this. I've tried many times to solve this, but I have no idea how to solve it. Okay, so an example of how you can do such a thing is starting with the form and then find the Riemannian structure. There is this conjecture by Taus. This is from 1994. Yes, 1994, which is now a theorem since 2011 that says that if you start with a three manifold, then you take the product of this three manifold with a circle, and this thing has a symplectic structure. This four manifold has a symplectic structure, not as one invariant, but a symplectic structure. Then N is a fibration over a circle. Okay? The fibers of this. What's way easier to prove is that if you add that the symplectic structure to be S1 invariant, okay, then you have not only the converse, but the other thing is really easy to prove. Not really easy, but it's easier to prove. So you have that three manifold that fibers over S1. This is true if and only if you have this S1 invariant symplectic structure, okay, on this thing. So to have a S1 invariant symplectic structure on this product is the same thing as asking for of having a symplectic mapping torus structure, which is to say that this vibration here and fibers over the circle in such a way that you have each of the fibers are symplectic manifolds, and you just twist them around and you glue them together through using a symplectomorphism. And the symplectomorphism is going to give you the twisting. So if just to show how you could apply this thing that I was mentioning, this structure that I was mentioning, if you start with a manifold of fibers over the circle, okay, you go here in the circle, you take the angle form, one form, okay, so it's a closed one form and it's non-vanishing. You pull it back by the vibration, so by the projection mapping, and you end up with a closed one form, which is non-vanishing on your three manifold, okay. There's a result by Calabi from 1968, okay, that says that we can find a Riemannian metric. So there's a Riemannian structure such that the hard star operator of this one form with respect to this Riemannian structure is a closed two form. Okay, and this is because we have this property of being non-vanishing, and this translates into, well, the work of Calab. This is a particular case of what he calls a transitive one form. Those transitive one forms are exactly the one form such that there exists a Riemannian structure making this thing here closed. Okay, and it's a technical condition. It's related to how he worked. He was trying to understand one forms as integrals of one forms as Morse functions, and try to develop some theory about the topology of the manifolds using these harmonic forms. Okay, and so you can conclude from that previous lemma what we start with this. We have this non-vanishing closed one form. We find a Riemannian structure, and we end up with this two form here. This two form here is closed. Okay, and this means that this, with respect to this two form here, we have a symplectic foliation, and the leaves are exactly going to be that are going to give us the mapping torus. We can work it a little bit, and we're going to have a proof of this result. Okay, we can work both ways around. It's possible. So this is going to be like a simple application of this that I just mentioned before. Okay. So what else can you get from this structure? If you have this two form, okay, which is non-negative, closed, and co-closed, this actually implies that once you make integrals of these two form, okay, so if you integrate this two form along some surface, you're always going to get a positive number, as long as you're getting surface which are positively oriented with respect to the Riemannian structure. Okay, because again, if you do not respect the orientation, everything goes wrong. You need to respect that, the initial orientation given by the Riemannian structure. And here's the proof of the theorem, which it's kind of simple. So let me show you an illustration. We start with our surface that we want. So we have the sigma here, and we want to integrate our two form omega over the surface. Okay, I choose the orientation of the surface to be positive with respect to the Riemannian structure. Okay, this is this arrow here, and at some point Q over this surface, there's going to be a leaf of the foliation defined by the kernel of the Hodge dual of the two form. Okay, and again, this is the orientation of the leaf, and because of the results that I mentioned before, this orientation is positive with respect to the Riemannian structure. So, and the contribution, so once you try to compute that integral, the contribution coming from this point here, it's a limiting thing, but again, you project this whole surface onto the symplectic leaf, and you compute the symplectic area of this projection. Okay, so you can see that even if you do the limit, you're going to see that the contribution coming from this point is positive. It's always positive. Whenever the kernel of the two form, explicit here by the R vector field, is transverse to the tangent of the surface that you're trying to integrate. If it's not transverse, okay, if it happens that the kernel of the two form is actually inside the tangent plane at this point here, for instance, in this sigma prime surface, in this Q prime point, what you get is going to get like a contribution, you're going to get zero, okay, because you're going to project this whole thing onto the symplectic leaf, and this is going to give you zero. Okay? So you either get a positive contribution or a zero contribution. This means that there is no negative contribution, so this integral is always positive. And you can call these non-negative Riemann class. So the Riemann class of this omega is non-negative with respect to the Riemannian structure. Okay, and let me see. Yeah, so it's really important to make sure that you're taking things positively oriented, because if you take some surface and you reverse the orientation, you're gonna get a negative number. But yeah, again, so it's those things only make sense when you fix previously the orientation. If you do not fix the orientation, there's no reason here. And the important fact is that the symplectic leaves, they are positively oriented with respect to the Riemannian magic that you start with. Okay, that's how these two orientations are tied in because of this equation. So if you do these for harmonic functions, you're gonna get something which is not, well, it's sort of won't surprise me, because so if you start with a harmonic function on a three-dimensional manifold, you look at the level sets of this harmonic function, those are going to be surface, and as we know, they are probably going to be symplectic, because as long as they are orientable, they are going to be symplectic. What is not that obvious is that if you take the Hodge dual of the exterior derivative of your harmonic function, this is actually going to provide you the symplectic structure, okay? And this comes from the fact that if you look at this two form, you take the Hodge dual of this thing, you're gonna get the one form, and the one form is exactly the exterior derivative of your harmonic function, and the kernel of these, which is defining the foliations, are going to be the level sets of the harmonic function. And from that theorem, you got that this class, the rank class of this thing, it's non-negative. Okay? And you know that this thing here is closed because it's a harmonic function. So the equation for a harmonic function is that this thing here is equal to the exterior derivative of this thing is 0. Okay? Same as being harmonic. In this particular case, the vector field R that I defined before is just the gradient vector field of a harmonic function. And then you can see that you have the vector field and then the orthogonal complement to it. So the level sets are going to be orthogonal to the vector field, which is obvious from the fact that it's a gradient, but in general it's also true. Even though we do not have things which are exact. I would mention Poisson equation as well to justify what I'm going to do next, but I rather do what I want to do next, and if I have time, I will explain something about this illustration here, which has something to do with the fact what happens if you choose things which are not positively oriented, and what goes wrong, and why everything is reasonable. But I'll talk about this later in case time. Again, I will mention really fast here is that everything here works even if you have zeros, okay? So the two form can have zeros, and everything, it's pretty much the theorems and the lemmas and everything, they work for the points where the two form is non-zero. But there's no problem to have zeros, okay? You just cannot say anything about those points, but they are not that relevant. Okay, so now the application, the thing that I want to actually do. So you have this two form, and this two form generates some geometry, and this forces the integrals of these two forms to be positive. So the idea is, if you can relate these two forms to a gravitational vector field, like in Newtonian gravity, then you can somehow show that gravitational mass cannot be negative. That was the idea behind this whole thing. Okay, so if we assume, so this is the definition, okay, that the space-like region is described by a three-dimensional orientable Riemannian manifold, and okay, this is reasonable. Think about Euclidean three-dimensional space, and also think about mathematics and geometry from and the next step, we define the gravitational source distribution as a subset of this space, Okay, so the subset is pretty much the points where there are matter, where matter is located. Okay, and this is also reasonable, and we have been doing this for a long time as well. So now what is not that obvious is that we're going to define a gravitational vector, a gravitational field as a closed-to form, define it only here on the complement of the set or where the sources are. Okay, so if you start with a compact manifold, you no longer have a compact manifold. Okay, so the complement is no longer compact, but that is not a problem. Well, it makes things difficult, but it's not a problem. So apart from asking these two forms to be closed, you ask these two forms to be coexact. That is, the Hodge dual of these two forms it's equal to the exterior derivative of something, okay, of a function. I'm asking a little bit more there, but this is equivalent. So now the next step is how do you define mass? So you do the same thing that you probably done when you're dealing with gravitational field using Gauss equations and the like. So a gravitational mass inside some region bounded by a surface, okay, is going to be this integral. So you take the two form, that is your gravitational field, you integrate it over the surface, and this gives you the mass. It only makes sense to take positively oriented surfaces. It's the same thing with Gaussian surfaces. If you take you have your gravitational vector field, you're going to integrate it along some surface, you choose some area. This area is positively oriented with respect to the equilibrium structure. Okay. If you take something which is negatively oriented, you have something else which is not a mass. So that's again a definition that makes sense. And the gravitational vector field.
Sorry,
Yes?
can I ask something?
Yes.
Can I ask something?
Yes.
Oh,
Yes.
I understand the condition of the gravitational mass or the definition of gravitational mass, but I don't understand your previous item, the condition for being a gravitational field. Why is
Okay.
the physical reason of that condition? Yeah, because the second one, the mass is because this Gauss theorem or whatever physics
Yes.
like to call Stokes theorem, but I don't understand physically this condition.
So this condition here, it's so if you look at the Gauss theory, you have a gravitational vector field, and this gravitational vector field must satisfy that the divergence of the vector field is zero, and what's the rotational? Sorry, divergence, and the other one is I forgot the name. Oh, the curl. Yeah, that's it. So the curl must be zero, and the divergence must be zero as well. Well, not zero both. Well, zero at the points where there's no source. Remember, I'm removing the source. Okay. So the gravitational vector field from the Gauss perspective is a vector field which is satisfies a Laplacian equation, sort of. So I want this two form to be a harmonic. Okay, and this is the condition. So I want this to be, it must be closed. This is related to the divergence of this function being zero at the points where there is no source. And I want it to be exact, like the dual, the Hodge dual of these two forms to be exact, is exactly as asking the curl of that vector field to be zero. Okay? So this is the curl of the vector field being zero, and this is the condition for the divergence of the vector field being zero when you have no source. Okay, remember I'm excluding the sources here from this. And the way you
like these conservative fields that they usually say.
Yeah, this is a conservative field. So, but how do you put it back? The way you put it back is through this definition. Okay, you need to reintroduce the source, and you reintroduce them like this. Okay,
Thank you.
So they are still there. They are not on this 2 form is not defined on the whole space, but this 2 form is not defined on the whole space because it's not defined over the points where you have the source, but it tells you what's happening outside the source. And that's all you need to know. You do not need to know what's happening inside the source. You actually have no idea how to access those points. If you think about it, you realize that there's no way you can know what's happening inside matter. Even if you go outside Newtonian mechanics. But anyway, but those are these two conditions. So to be closed is related to the divergence vector field. Okay, this R vector field, which is the gravitational vector field, is divergent free, and to be co-exact means that this vector field is also there's no vorticity. Okay, in this vector field. So okay, so the next definition, which is already mentioned here, is that the gravitational vector field is going to be the solution to this equation. So it's the dual to minus the hard star of the 2 form. If you work in units which make sense, there's going to be the gravitational constant here divided by 4 pi. Okay? Otherwise, you just use units, physical units, where the gravitational constant is 1 over 4 pi, and then you get this equation exactly. And lastly, you have this condition that we all know from Newton, that the force, so you have a test particle, okay, of gravitational mass m, and it's going to be influenced by gravitational field through this force given by your mass multiplied by the gravitational vector field. Okay, so there's nothing new here. There's nothing new here. There's nothing new here. Neither here. The only thing new, sort of new, is this. Okay, to describe gravitational field as a closed 2 form instead of describing it directly as a vector field. Okay, and what do you get out of it? So if you apply to the simple example possible, which is a point particle in the middle of the Euclidean space, so we have the 3-dimensional Euclidean space. You look at the origin and you put some matter there. You do not know what it is. You just put it there and you're going to investigate if it makes sense, this whole theory or not. Okay. So in this particular case, you know that the second homology group of the Euclidean space minus a point is just isomorphic to the one-dimensional vector field, or vector space, sorry. And any element here can be represented by a 2 form written this way, okay, which is just some real number times this 2 form here, which is the area form of this field. Okay? And this 2 form happens to be co-exact. So if you take the Hodge dual of this 2 form, it's really easy to see that this thing here is going to be the exterior derivative of the function. And the Dirac class, so in particular, this thing is also closed. The Dirac class of this thing generates the whole space here, the whole homology group. And you're basically, in this isomorphism here that I'm showing, it's basically to choose this as a basis. Okay. So what's the next step? If you take a 2 form like this one, any 2 form which is just a multiple of this thing, of this generator, you integrate it over some sphere, positively oriented as well, that contains the origin, you're gonna get this number, this real number. Okay, let me see. And if you suppose, okay, now it's the supposition that this 2 form is a gravitational field. Gravitational field in that sense that I just defined. Then if you compute the gravitational vector field, you're gonna end up finding exactly what to expect. Okay, this is actually what Newton just started with. And here you see the mass. So this is going to be related to the mass of the particle. Okay, and because by definition, this thing here, the Hodge dual of this thing gives 0 symplectic leaves, that theorem 1 tells us that, tells us that this integral here is actually the symplectic area of this sphere. And this is even clearer because now this vector field R is the radial vector field, so the leaves are going to be the spheres, okay, which are perpendicular to this radial vector field. So this integral here must be the symplectic area of the spheres, and this thing must be positive. There's no way it can be anything other than positive if omega is a gravitational field as defined. So the conclusion is, if this number here is negative, then there's no way this two form can represent a gravitational vector field. Okay, so what's yeah, I think I have someone to say this. Yeah, so just to make sure that there's no confusion here, the isomorphism that I use it's not relevant. Okay, it's kind of obvious, but I want to make sure here because I've been tested this before. So if you take another isomorphism between your cohomology group and the one-dimensional vector space, for example, you take this one, okay? If you compute the integral of some two form being represented by this number here, okay, it's going to give you this number. So it's a negative m tilde over 5, okay? And if you know this is negative, yeah, but theorem 1 tells us that this integral, this whole integral is positive, no matter what. So if I change the isomorphisms here, this number is still positive, okay? So there's nothing to do with the choices that I'm making here. So what's the summary of this whole thing? So if we have some assumptions, like these 5 assumptions, and I do not explain them, and that there's no need to explain them, there's no need to prove the assumptions, those are assumptions, okay? Most of these assumptions, we are already using it for centuries now, and the only new thing here is the fact that we are describing the gravitational vector field as a closed and co-exact differential 2 form. This is the only difference, maybe, from the rest is things that we are using centuries ago. And the fact that this 2 form has this structure of this symplectic foliation, and the symplectic leaves are positively oriented with respect to the original Riemannian structure, this implies this fact that the gravitational mass cannot be negative, okay? And so, although I do not claim that I'm able to prove that this condition here makes sense, what I can claim is that the predictions out of these assumptions, they do make sense. And the predictions are that we have the Newton's theory, okay, so 2 particles with gravitational mass, they interact via multiplication by the masses and the square inverse of the distance. We also have this thing that, well, we have no idea how to, well, this is a way to see that gravitational mass cannot be negative, okay? And we got linearity with respect to the source, so if we have, I just show one example with 1 point particle at the origin, but if you have many point particles, you have that these homology groups and homology groups and everything is linear, including the equations that the 2 forms satisfy are linear. So everything is linear, so you just sum everything, it works. This is what is expected. And if you change point particles by something with volume, so you have Newton's shell theorem, this comes out from the fact that we are working with the homology groups and homology groups, and those are invariant by the topology of the manifold. So R3 minus a point and R3 minus some 3-dimensional volume that it's homotopic to a point in the same thing. So this is what you get. And I have no idea if I have time to talk about this, but I will end here. And if someone wants to ask me about what happened with other things, I can explain. So that's it. Yeah, that's it. So let me give it to you people.
Thank you very much.
We have to buy you a microphone.
No, the problem is not a microphone. I do have a microphone.
I have a headache now.
The problem is to decouple the microphone from the sound of the fan. That's my problem. So are there any questions, or can we go?
Joachim, the chairman. You are the chairman. No? Chairman.
Yeah, we have had several questions during the talk, but feel free to keep them coming, of course.
I have a question, Romero, but regarding a thing that you haven't explained, so maybe you can explain now. In the picture, you passed fast. In one of them, there appeared a blue and a red part, but
Yes.
I assume this is not gravitational, but electromagnetic. What's exactly that picture?
So, okay. So that picture is actually about Poisson equation. So, really fast here. So everything I said, it's about Laplace's equation. Okay, so it's harmonic functions, harmonic differential forms, and there's no source. But if you, and I'm claiming here that I can do something when there is sources. Okay, but we all know that if you have a Poisson equation, like here, the source can be negative or positive. You have solutions for negative. You have negative solutions and positive solutions, and they do exist. And actually, you have solutions where your source distribution or function is positive at some points and negative at others, and this all makes sense. Okay, so what's the catch? So this contradicts the fact that you have something which is that thing here, that the rank class of this thing is always non-negative. So the catch is the following: if you start with something that is a positive source and a negative source, okay, the leaves, so the foliation, you still have a foliation, okay, given by, so this is 2 points, a negative source and a positive source, and you have some function, and this function satisfies this Poisson equation, and this Poisson equations end up being Laplace equation everywhere but over these points, these 2 points. So you have a harmonic function, and you're looking to the level sets of this harmonic function, okay? In this case, the level sets are going to be spheres around each of these points until you reach a plane, okay? So we are in three-dimensional Euclidean space, and you have these spheres on one side, the spheres on the other side, and then they meet over a plane, which is also a leaf of this foliation. But in this foliation, so those are surface, so they are all symplectic surface. But what they are not is symplectic with respect to the same symplectic structure. Everything that is on this side of the plane is going to be symplectic with respect to omega. Everything that is going to be the other side is going to be symplectic with respect to minus omega. Okay, and this plane has this particularity that being symplectic with respect to both structures. I guess. Yeah, I guess. No, well, there's an orientation here, so I think it's only, yeah. So I think it's only with respect to the omega, not minus omega. So you see, there is no one two form that wholly restricts to a symplectic form on each of the leaves. There are actually two forms, omega and minus omega. So this is why this is not compatible with negative source. You can still describe things, but you cannot have, so the structure of this geometric structure does no longer hold like globally in the whole manifold. And this is pretty much what you get in, so okay, these structures are what it's called a regular current one Poisson structure, okay? In the case of everything is positive, but when things are negative, they're still current one, right? Regular. What they are not is because if you include those points here, then they are no longer regular. But again, you have this, so it's work. And if you want to try to use these assumptions here, if you change everything by everywhere that is written gravitational, if you put electric, and then where is mass, you put charge, you're gonna end up with a theory where there is no negative charge, only positive. So you're pretty sure that these assumptions are terrible to describe electrostatics. But again, there's no problem because you just do not use these assumptions for electrostatics, use other ones. And this is what we actually use because we actually abandoned trying to describe electrostatics using two-dimensional manifolds, and we now use four-dimensional manifolds to describe them, and we use electromagnetism instead, and blah, blah, blah. But again, yeah, that's all I have to say about this picture here, and how you can deal with Poisson's equation instead of Laplace equation.
Okay, thank you, Romero.
And what is the physical interpretation of the fact that this symplectic foliation is preserved?
Sorry, Robert, can you?
What is the interpretation of the fact that you have this symplectic foliation which is preserved, no, by the flow?
Paul, can you tell me what Robert's trying to say? The microphone is not
right. My microphone is really bad. So.
Yeah, no, but Paul can tell me.
Now you can hear me better.
Paul is right here with you, right? What did Robert say?
Can you hear me now?
Yes, now I can hear you.
Yeah, because yeah, it's okay. So my question was that. So what's the physical interpretation of the fact that this symplectic foliation is being preserved by the flow?
By the Rev vector field, this Rev vector field.
Well, this is the gravitational, no?
Yeah, this
the
is
same one.
Yeah, what you have this R is okay. So if you have a two form and a one form, okay, and they are non-vanishing, and their product is going to give you a volume form and a three manifold, you have almost contact structure, right? And this almost contact structure has you can define a red vector field for it, and this is exactly the direction of this red vector field is going to be exactly the direction of this gravitational vector field R that I defined. Okay? So this is the same. In this particular case, since you have that the foliation is integral, so the distribution is integral, so it's the opposite case of the contact, so it's something that is actually non-contact is far from contact as possible, but still being almost contact. So you only have this grab direction is transverse to the symplectic leaves, and I think we do not have any extra physical information from this apart from the fact that
so the foliation is not preserved by the red flow.
No, by the gravitational vector field. No, it's transverse. It's always transverse. What you get is this.
I see.
Yeah. What you get is that is the level sets of the harmonic function.
But the Poisson structure is preserved. This is what Robert wants to say.
No, yeah. So what I mean is, aren't leaves sent to leaves or something like
this? The leaves are sent to leaves, and there is some kind of volume, and the volume is defined by omega wedge alpha, or this one form, has to be preserved. I think this is what Robert is asking.
So my question was if there was an interpretation of the fact that these leaves are
Yeah, this is what you. This is from where you get the fact that the mass it's always going to be positive, as well the fact that we can use any Gaussian surface to measure the mass. So you go to the source, and if you take a different Gaussian surface, you're going to have the same interval because the volume is preserved. See, so if you take something that is really small or something that is really big, the ending result is going to be the same because you adapt to the fact that now the area is bigger, but the two form is weaker, so to say. So you're spreading the information, the symplectic information.
Okay, I see.
Yeah, I think that there's no. Yeah, the volume is preserved by the gravitational flow. It's just that it's again the fact that you have something which is the curl is equal to 0 and is divergence free. So yeah, you have something that is expanding and that there is no like twisting of the thing.
Okay, thanks.
Are there more questions? Well, if there are no more questions, thank you again, Romero, for this first talk of the reiteration of the seminar.